Next speaker, he's actually a very good, close colleague of mine and my best friend, Mitch Joachim. So a little bit of background of Mitch Joachim. It would take me a long time to describe all his major accomplishments, so I'm just going to abbreviate it here. Dr. Mitchell Joachim is a leader in ecological design and architectural design, architecture and urbanism. He's the founding co-president of Terreform ONE. Mitch is an associate professor at NYU and EGS in Switzerland. He won the Zumtobel Group Award for Sustainability and Humanity, the Victor Papanek Social Design Award, and Time Magazine Best Invention with MIT Smart Cities. He was chosen by Wired Magazines for the Smart List 15 People the Next President Should Listen to. Rolling Stone magazine honored Mitchell in the 100 People Are Changing America. He earned a PhD at Massachusetts Institute of Technology, MAUD Harvard University, MArch Columbia University, and he's also a former roommate of mine. Mitch?
Thanks, Oliver. Thank you to Oliver and Ellen. Super great to be here. We're all actually from Brooklyn, New York. We're in one large hackerspace called the Metropolitan Exchange, where we do work together. We actually mix disciplines, whether you're doing mechanical engineering, architecture, planning, cellular biology, synth bio, it's all happening there. So you're welcome to come to Brooklyn. Projects that I work on at Terreform ONE, which is our nonprofit company, are about thinking of the future of the city and what are some of the materials and resources that make it truly ecological. This project here was for the cover of Popular Science, where we're rethinking transportation in different modalities. So there's your kind of jetpacks and blimps, which were some things we worked on, but not to be glib, I'm not going to show them. We're going to kind of concentrate on things that look at the discipline itself. What makes up someone that should change cities? Who are the people that should actually affect them? And the answer is the community, the neighborhood, the people that are there already. This is kind of a coalition of top down and bottom up. So people that do act on cities, we've got a name for. They're called urbaneers. And it's a kind of a mixture of Jane Jacobs and Robert Moses. So if you can imagine the two of them making love, which I don't know if that's possible, but the power broker and the kind of the neighborhood watch person, you would get someone that'd be very different. Someone that has all the power and the agency to make change, but someone that cares directly and is focused in on the community simultaneously. And that develops a new profession. We call it an urbaneer. Frederick Law Olmsted would be one kind of an example. And the city itself, changing the kind of semiotic pulse of what we think about when we think of our future ecological city. So here we're moving from current city centers, which are centered on the idea of cathedrals or ecclesiastical artifacts or places of worship, to what we find today. The city center is the kind of the industrial city center, or in skyscrapers to celebrate commerce becomes a kind of spectacle of the city, to what we think the future city should be, which is celebrating the stuff of life, the spectacle of infrastructure working really well to bring us waste, food, water, energy, moving things on time, etc. And that's the kind of direction we see for the next century of cities. And that means a whole lot of things happen. So we create these diagrams. I'm not going to show them all, but they help people of the community to come together as urbaneers and affect their city, work on particular neighborhoods to create change under this rubric of looking at it through the lens or filter of ecology. So here is an example of downtown Brooklyn, dividing it up into quadrants, different forms of energy, cap the population, and then translating it together in a physical model with the people that are invested in their neighborhoods, with the architects and planners and members of government working in one space and arguing, having a polemic about what should happen in a particular area. And then those models become sketches of a projection of what that city might be, then goes back to further analysis. Here are some areas about thinking that we want Central Park to turn into an area to produce, not just for leisure, but an area that produces algae and biofuel. This is an area down in the Brooklyn Navy Yard. We're working on a project down there with New Lab. This is essentially translating the difference between water's edge, issues of flooding, dry docks, and usable spaces for people. Showing some of the plans there with turbidity barriers and areas for studying limnology and riparian corridors, as well as ship repair. Here's a kind of a phase in on some of those areas. We're imagining using depleted vessels or ghost fleets, old relic ships, and sinking them in the water to create a soft barrier between the edge of the city or the peri-urban condition and the actual land. So instead of hard dams that separate water from people, we do believe there should be a lot of these kind of interstitial wet zones make up those areas, and they could become something like this particular zone here. in downtown, and then showing that the landscape and the architecture is one and the same, is absolutely fluid. For those familiar with landscape urbanism, this is similar in theory. Buildings also develop to be, thinking about skins that are low in energy to develop. Here, a diagrid system for a green tech or clean tech office space. This is an overview of the entire area down in the Brooklyn Navy Yard, showing some of those dry docks, and the new lab building is in the corner over there. And then here, this kind of central piece for this particular city, when you start developing it over time, doesn't become skyscrapers or cathedrals or religion and commerce being the center of the city, but here the city center is those ecological needs. In this case, it would be a waste to energy plant, would be something that the citizens would be proud of. They can point to it and say, we actually understand our connection to the earth and the metabolism and resources of the planet. And then other projects that we've been working on about things that flow through the city, because we work at all different scales. I'm going to slowly get smaller to the molecular scale. Here is something called the soft car. It's a project that's rethinking mobility, where no one will ever die in a car accident again. So this is called the hug and kiss lamb car version. If it hits your sister, it tickles her, it doesn't kill her. It's designed to fit into downtown cores. It moves in flocks and herds. It's intelligently linked to one another. It could be autonomous. And when it finds a big, nasty Hummer on the road, it clusters around it and pushes it off to the side as these take over the streets. And we've, of course, produced one. This is at MIT. This one you could buy. It's called Heroku. This was developed in the Basque countrysides with Korean money, but there's a stackable car that's linked and moves in herds. That later. Other projects are thinking about how to be absolutely green when it comes to thinking about cities. So here is taking a technology that's been around for 2,500 years. It's called pleaching, or grafting inosculate matter to form one contiguous structure, or a linked tree or grafted tree, any kind of woody plant. We more or less do it. There's over 50 species. In this particular case, the house is the landscape and the landscape is the house. And it's contributing positively to the environment, not taking away or not a zero-sum game, but it's actually producing oxygen, taking away carbon. Here's kind of the model that we did for the MoMA, showing that's growing. Obviously, it takes a modicum of time to do these things. We think time is okay. If you wait 12 years to drink a bottle of scotch, I think you can wait 12 years to grow a village that can house about thousands of families. And then finally, kind of the lab space work that we've been doing with GenSpace Terreform. This is the lab that was shown. We worked on this project called the in vitro meat habitat. Is intended to be kind of a propaganda piece, but showing what you could do with when you think about biology and industrial design combined. So Oliver's student at Harvard was working on a modified inkjet printer that can print mammalian cells or extracellular matrix from pigs into a specific shape, fold it up on scaffolds and produce these things like bladders. We were thinking, what else can we do with it? Certainly you can make shoes, leather handbags, belts where no victim is harmed, kind of victimless products, although Orrin Katz believes that at some point you are taking cells from an animal, but essentially it is a victimless product, super green, grown in the lab, and then we could think about what scale we can produce it at. In this case, a house. This is my favorite section in architecture, which, is that a laser? Okay, you can see a typical American suburban house on one side, and then on the other side is the meat house, where we're using fatty cells for insulation, cilia for wind loading, and sphincter muscles for doors and windows. And there's a kind of the concept of the home. It could be anything that we wanted it to be, because geometry didn't matter when you can design it to be any particular shape. So we knew this one was particularly ugly, although it could have been a Spanish colonial or an English Tudor. Here's another kind of version that we're showing that what the final model would be. We know the limitations of the technology. If we didn't start a lab and build it from scratch, and architects and biologists working side by side, we'd have no idea how to do it in the first place. So we're constantly using it to push other ideas, and that led to our chair project. Oh, and then we had a big show in Prague, so we put the meat house in front of the cathedral so religion can confront the house of meat. And looking at waste systems, which are also a part of it. I think that this is showing that you can use off-the-shelf technologies, modify their jaws so that they can put waste into specific shapes, and show the average American how much damage we do to the environment or how much resources we use. So in this case, we're showing 36,000 tons of trash per day. produced in 24 hours in New York City. This is 1 hour of waste in the city of New York, which is the scale and size of the Statue of Liberty. And we took that technology into the lab, taking waste you'd find in landfills and using it as food, in this case for mycelium, to grow geometries, to grow usable objects or surfaces or spaces or puzzle-fitting blocks. This was for a show for the New Museum of Contemporary Art, thus the shape. In 7 days, we went from basically waste material or ash into a grown mushroom that was square and blocky, which is pretty cool. And this is kind of, that's showing if you combine it with something like aluminum, which is endlessly recyclable, you get more shear and get a much more intensive product to be built into something maybe like this. Where does this go? Which is what we call a 24-hour tower. This is a 53-story skyscraper produced in 1 day in the city of New York, just from its waste as a proposition. And we went to Darmstadt, we took students, we used e-waste, we showed how much e-waste is used in the city in just 1 week. We made these little robots mimicking the previous project with QR tags so people can learn about what they do when they throw out electronic waste. And here they are down in the square in Darmstadt. And this is the sanitation guys taking a look at it, deciding whether they were art or trash. And they were just kind of cycling around them, and they eventually want to throw them out. And then finally, the project that GenSpace and us have been working on for the International Genetics Engineering Machine Conference, iGEM, this is called Gen2 Seat, Genetic Generation Seat. It was a large team, 30-something people from all kinds of disciplines, including a creative writer who seemed to be the most dominant in architecture and biology somehow, but a fantastic kid. And we worked together coming up with a new biopolymer, a kind of a material that's a combination of the mushrooms before and then cellulose or acetobacter, basically expressing this, doing it from, expressing cellulose from kombucha tea. We can grow a kind of a sheet that wraps around the mushrooms, then express something else like keratin or fingernails, I guess it would be the more simple way, make it more waterproof, and design it to be an object. We had these 3D Petri dishes. We can make them into Tetris-like shapes. Here we're showing the different layers and components that go into making this biopolymer, showing the different growth cycles. In 7 days, it kind of fits out, and you can get your object. This is testing the cellulose from the kombucha tea. And this is kind of the geometry we decided again. Again, we don't have the ability now to control genetically forms or shapes. It's simply not possible. HOX genetics is the closest we can get to it, and they're still 15 years out. But we chose this form as a kind of a coccyx or a seat for your backbone. And this is the shape. This is what we can grow in a lab. Excuse me. It's a kind of a seat originally intended for children, but now we'll go full scale, and we'll be manufacturing this thing shortly. And this is showing my daughter sitting on the chair, and it's perfect for kids. And I think what's important to remember is this is not, there's a radical difference in the thinking of design. It's not your, kind of a colonial chair, this kind of bespoke, crafted, one-off object. And it's certainly not something from mid-century modernism created by Charles and Ray Eames and Saarinen in the Bauhaus, which is still the dominant paradigm. It's fantastic, but it's a very different method about looking at design and craft in general. This is something that's grown in a lab. It is truly organic, not your grandpa's version of organic design, which still included fiberglass and steel and aluminum. This is actually grown and produced in vitro, or using different fungal systems. And when you're done with this particular chair, which it does have a life, it has a life that contributes beyond just its own single human function. It ends up in a garden and contributes to other organisms, worms, the soil, other points of life, not just for humans. When you buy an IKEA chair and throw it out for 3 years, you keep this one forever. Anyway, I don't have any more time, but thank you very much for listening. See you at the party later.